G'day my smart mates, my name's Dylan Dance. Grab a coffee. Actually, where is my coffee? Grab a coffee, grab a chair, grab a Vegemite sandwich. Look, grab whatever you want to grab. Let's talk some natural philosophy. Alright, so this guy's moving his fist so fast that he is lighting the air on fire. Could you really do that? Yes, you could. And it only takes about Mach 8 to achieve. So if you were to launch your fist about 2,720 meters per second, you would light the air on fire around it. Pretty cool, huh? We could do that. But I mean, you know, you're probably gonna die. Alright, is it possible to be in more than one place at the same time and have like 3 of you? Yes, it is actually possible if you're a particle. So down in the quantum world, things get very weird, and particles have this property where they can be in more than one place at the same time. It's called superposition. And in fact, they can be in not just more than one place, they can be in every place at the same time. So in the quantum world, we calculate probabilities. And it turns out that, say, an electron around an atom actually has a non-zero probability of being pretty much everywhere at the same time. We call this the probability cloud. And so that's what I meant in the Dr. Stone video when I said electrons don't really orbit. They're not moving around the nucleus. And I didn't explain it and people got a bit annoyed. So what I mean is it's not orbiting. It's just kind of everywhere at the same time in this probability cloud. So it's not until you take a quantum measurement of the system and you have a look where the electron is that the electron actually decides to be somewhere and only there. It's what we call wave function collapse. Yep, they lied to you in school. There's nothing really whizzing around an atom. It's far more complicated than that. So could a human being, a macroscopic, a large object be in more than one place at the same time? Could it use these quantum properties? And no, we don't think so. So objects lose their quantumness as they get bigger. So down on the very small scale, there are lots of weird things happening like this superposition and even stranger things. But as you zoom out, things seemingly lose this property. Wondershare Filmora have sponsored this video, so a massive thanks to them. More than happy to vouch for them because it's the very video editing software I use to make all of these videos. So go down in the description and there's a link to download Wondershare Filmora for free. Yes, free, Mac or Windows. If you're like every other human on Earth right now wanting to make a YouTube, well, you need a great, efficient video editing software. And a lot of them can be super expensive, complicated to use, and they require all sorts of third-party extensions to do what Wondershare Filmora can already do. Filmora is very straightforward to use and it has a lot of unique features like key farming, which is where you can control where an object goes in every single frame, motion tracking, where an object can follow anything, and a ton of great effects that you can easily get. They also have an iPhone app called Filmora Go, which is nice. They have 2 other products too, apart from Wondershare Filmora Pro, which is their professional video editing software. They have Video Solutions for Business, which is a great way to share your brand, and Wondershare Film Stock, which are effect packs. So once again, thanks to Wondershare Filmora for sponsoring this video. If you go down in the description, you can get Wondershare Filmora for free on Mac or Windows, and just by checking it out, you'd be helping me out and this channel out enormously. So this guy looks extremely edgy. Got no idea what's going on here. I'm lost. Confusion. Alright, he just threw him. He's flying across the water. Breaking a lot of rocks. All right, we could probably do some sort of calculation there. He just got thrown across the planet. I don't know about you, but I think they just broke a bunch of the laws of physics. And I'm not about to let that slide. So let's analyze this scene here. So that guy went flying. There's a rock here about 3 times the size of him. So maybe about 3 cubic meters. And let's assume limestone. You generally find this sedimentary rock in coastal regions. So the strength to break that sort of rock is about 2,000 newtons. So doing the calculations to work out how much strength is required to break that rock works out to be about 2,000 newtons for every cubic centimeter on the side of impact. Assuming a cubic rock, that's about 60 million newtons just to break that rock. To put that into reference, I'm pretty sure the strongest force generated by a martial artist was about 10,000 newtons. So you do the math. That's a pretty strong guy. So I took out the ugliness, like the surface area, the density, because that's how we do in physics, and just assumed it was a moving object of about 70 kilograms, about the average male weight. So let's take this a bit further. If this edgy pain guy was to just break the rock and have both objects at rest after the collision, side note, I used 1 frame of television, about 1/20th of a second as the collision time. Again, to simply just break the rock, he would need to be moving at 43,000 meters per second, or 96,000 miles per hour. So a little reality check here, and to give some perspective, the Earth is moving around the sun at about 65,000 miles per hour. And the escape velocity of Earth is only about 25,000 miles per hour. So you travel faster than that, and you can say bye-bye to Earth. So if Naruto was really to get pushed like that, he would be off into space, and he'd actually have enough energy to make it to about Saturn before falling into an orbit around the sun. So we can actually relate this back to some real science right here, because have you ever had a look at the moon and noticed that all of the craters are round? That's a bit strange, right? Because you can imagine comets or asteroids hitting the moon at an angle, right? And if they hit at an angle, you'd expect, some sort of long crater. You wouldn't expect to find a round crater, would you? But we only find round craters, and this was a big mystery for a long time. So we used to actually think that all these craters were round because they weren't actually craters. They were ancient volcanoes. We saw a giant comet hit Jupiter. That doesn't make a lot of sense, because if you know much about Jupiter, you know that it doesn't really have much of a surface. It's a gas giant. It's made of gas. You could fly through Jupiter. It is literally just gas. Yet we saw a comet hit Jupiter and explode. And what happened here, what we realized, is if something is traveling with more kinetic energy than chemical energy holding it together, as soon as it hits something, it just explodes. It dumps all that energy. And that's what we saw happening here. So what is happening on the moon is when things come in and hit the moon at angles, they're actually traveling so fast generally that they just explode. If you live in an area of snow, you can actually see this in action. So you can make a little snowball, throw it at the wall, and it will leave a circular imprint on the wall. Now throw it at the wall on an angle. If you throw the snowball at an angle at the wall, it explodes on impact because it's traveling with more energy than energy holding it together. So what happens, it hits the wall at an angle and just explodes, and it leaves a round imprint. Isn't that amazing? It's also related to how if you were to jump off a bridge and you're traveling very fast now and you hit water at a very fast speed, the water molecules don't have enough time to get out of the way. And so it's like hitting concrete. And the same is true if you hit an atmosphere of a planet. If something was traveling fast enough. So, you could theoretically do this with anything. You could throw a planet, and if you throw it fast enough, it will explode on impact. The famous Naruto run. So if you were to position your body like that and run, would you actually run faster than, a normal running style? And you actually would, because, it's simple aerodynamics. Running like that, you're going to just be more aerodynamic. So if you scale that up, the speeds at which we can move at, you would actually be far more aerodynamic and you would travel a lot faster. But it probably doesn't come into play very much with the speeds, the velocities we can travel at. So But yeah, I can tell you that's kind of obvious. You don't really need to do any calculations there. Just taking a big old dump on physics, aren't they? Yeah, I wouldn't try walking up a tree. You're not going to get very far. Serves him right for breaking the laws of physics. Alright, that'll do it for this video. Please subscribe and like. Follow me on Instagram for memes. And a huge thanks to Wondershare Filmora for sponsoring this video. Description, click on the link, helps me out.